Imagine you're blindfolded on a mountain at night. Your mission? Find the lowest valley. You can't see the entire landscape. You can only feel the ground beneath your feet. What do? You feel which way is downhill and take a step. Then repeat. Step by step, following the slope, you descend toward the bottom. This simple strategy, it's the exact algorithm that trains every neural network you've ever used. ChatGPT, DALL-E, self-driving cars, all of them. It's called gradient descent. And in the next 5 minutes, you'll understand it from the ground up. The math, the intuition, the advanced techniques, and why it's both brilliant and broken. Let's build this from first principles. Start with a simple function. F of x equals x squared, a perfect parabola. At any point x, the derivative tells us the slope. Positive slope, function increasing. Negative slope, function decreasing. Zero slope, you've found the minimum. The gradient is just the multidimensional version of the derivative. It's a vector pointing in the direction of steepest ascent. Think of it as an arrow showing this way up, but we want to go down, so we do the opposite. Subtract the gradient. The formula is x new equals x old minus learning rate times gradient. 3 components. Current position x, the gradient, which way is up, and the learning rate, how big of a step to take. That's it, that's gradient descent. Move opposite to the gradient, repeat until you reach the bottom. But here's where it gets tricky, the learning rate. This single number controls everything. Too small, your algorithm takes baby steps. It'll eventually reach the minimum in 1,000 years. Painfully slow convergence. Too large, you overshoot. You jump past the minimum, then overshoot back, bouncing around like a pinball. You might never converge, or worse, diverge completely, shooting off to infinity. Just right, smooth, fast convergence. But finding that perfect learning rate, that's an art and a science. Watch what happens with different rates on the same function. Real machine learning isn't a simple parabola. It's a complex, multidimensional landscape with hills, valleys, and saddle points. Imagine a mountain range with multiple valleys, some shallow, some deep. The deepest one is the global minimum, the best solution. But there are also local minima, valleys that look like the bottom but aren't. Gradient descent is greedy, it only sees the local slope, so it can get trapped in a local minimum, never finding the true best solution. Even worse, saddle points. Places that look flat, like a minimum, but are actually high in some directions. The algorithm can get stuck here, confused about which way to go. And then there's the plateau problem. Flat regions where the gradient is nearly zero. The algorithm crawls at a snail's pace, wasting time in the desert. Researchers knew vanilla gradient descent had problems, so they invented variants. Let me show you the 3 game changers. First, stochastic gradient descent. Instead of computing the gradient using all your data, millions of training examples, you use just one random example at a time. It's noisy, it's jittery, but it's fast. And that noise, it actually helps escape local minima. Second, momentum. Imagine rolling a ball downhill. It builds up speed. Even if it hits a small uphill bump, the momentum carries it through. Same principle here. We add a velocity term that accumulates gradient information from previous steps. This smooths out oscillations and speeds up convergence. The formula adds a momentum term, v equals beta times v old plus gradient, then update, x minus learning rate times v. Beta is usually 0.9, meaning 90% of the old velocity carries forward. Third, atom, the current champion. It combines momentum with adaptive learning rates. It keeps a running average of both gradients and squared gradients. This lets it automatically adjust the step size for each parameter independently. Atom is so good, it's the default optimizer in almost every deep learning library. PyTorch, TensorFlow, JAX, they all recommend Atom first. Let's see gradient descent in action, training a real neural network. We have a network with thousands of parameters, weights, and biases. Our goal, minimize the loss function. This measures how wrong our predictions are. Here's the process. Forward pass. Input data flows through the network, producing predictions. Compute loss. Compare predictions to true labels. Backward pass. This is where gradient descent happens. We compute the gradient of the loss with respect to every parameter using backpropagation. Now the magic. Update all parameters simultaneously using gradient descent. Each weight moves slightly in the direction that reduces loss. Repeat this millions of times. Each iteration, the loss gets smaller. The predictions get better. The network learns. Watch the loss curve. It starts high, the network is guessing randomly. Then it drops rapidly as gradient descent finds patterns. Eventually it plateaus, the network has learned as much as it can from this data. This is how every deep learning model is trained. GPT-4, gradient descent on 175 billion parameters. DALL-E, gradient descent. AlphaGo, gradient descent. It's the algorithm that powers modern AI. But gradient descent isn't perfect. It's a greedy, local algorithm. It can't see the big picture. The challenge requires gradients, so your function must be differentiable. Get stuck in local minima. Sensitive to initialization. Start in the wrong place, you'll find a bad solution. Needs careful tuning of learning rates and hyperparameters. Researchers are working on alternatives. Evolutionary algorithms that don't need gradients. Bayesian optimization for hyperparameter tuning. Second-order methods that use curvature information. But here's the truth. Despite its flaws, gradient descent works. It scales to billions of parameters. It's computationally efficient, and most importantly, it generalizes. The solutions it finds actually work in the real world. So the next time you use ChatGPT, remember, behind those intelligent responses is a blindfolded algorithm, feeling its way down a mountain, one small step at a time. That's gradient descent. Simple, powerful, everywhere.